I'd like to now discuss some of the shapes that we need to be aware of when we talk about valence shell electron pair repulsion theory. Now remember, in each of these cases, the shapes are going to be defined by the notion that all atoms around the central atom are going to try and be as far apart from each other as they possibly can be, and this will end up defining the shape of each of these examples. In the first one, we're going to talk about a situation where we've got a central atom and then two things attached. The shape for this is going to be called linear, and we're going to look at carbon dioxide or CO2. And this is what CO2 is going to look like. As you can see, if you wanted to have two things around the central atom, the way you would arrange it would be with 180 degrees apart to make these oxygens as far apart from each other as they possibly can be. And here you've got the carbon in the middle, so you can see that's a linear shape right there. In the next one, we're going to talk about what happens when we have three groups around the central atom, and that shape is going to be called trigonal planar. And again, the reason for this is that we've got three fluorines around the boron here, and in order to make them as far apart as possible from each other, we arranged them in a triangular type arrangement. 120 degree bond angles, all in the same plane. See, they're all in the same plane. So if you wanted to have three objects as far apart from each other as possible, this is how you would do it. Alright, let's look at what happens if you've got four things around the central atom, and we're looking at a tetrahedral shape now. Now a tetrahedron is a four-sided figure, and these atoms would be at the vertices of such a four-sided figure. Let me show you what a tetrahedron looks like. It's a four-sided figure that has equilateral triangles for each of its four sides. There we go. So that's what a tetrahedron would look like, and if we're talking about tetrahedral shape, what you've got to imagine is that there's an atom in the center of this four-sided figure, and that we've got atoms at each of these vertices. And the overall shape of that would be called tetrahedral. Alright, so here's an example. This is CH4, and as you can see, we've got a shape now that is no longer planar, it is three-dimensional. Now what I'm going to do is I'm going to arrange it so these two are actually in the plane of the screen, and what you'll see is that this one's sticking out and this one's sticking into the screen. When you do the math on this, what you'll find is that the bond angles are all 109.5 degrees. And that's what a typical tetrahedral bond angle is going to look like. Alright, so there you go. So that's CH4. And again, the reason that these are all arranged like this is that if you want to put four hydrogens around the carbon, they want to be as far apart from each other as possible, and this will be the arrangement that they'll take. Alright, let's take a look at the next one where we've got five groups around the central atom, and the shape we're going to be looking at is called Trigonal Bipyramidal, and this is it here. And what you'll notice is that it's sort of a combination of a linear shape, because you've got a linear geometry here, and a trigonal geometry here in this plane. So if you have got five items you want to put around a central atom, this would be the way you would do it, and in this way everything's as far apart from each other as it possibly can be. The name trigonal bipyramid or trigonal bipyramidal comes about because if you look at the four atoms here, they take on the shape of a triangular based pyramid. So there's your triangle on the bottom, and there's the tip of the pyramid right there. And it's a trigonal bipyramid because you've got a pyramid up here and a pyramid on the bottom. So that's where the name comes in. Right, so again, we've got a linear geometry here and a trigonal geometry in the plane, and the bond angles would be 90 degrees between this one, and you'd have 120 degree bond angles between the ones that are in the same plane. And if you like, you can say we have a 180-degree bond angle between here and here. Alright, let's take a look at what happens now if we have 6 atoms around a central atom, and that geometry is going to be called octahedral. Now I know what some of you are saying, octahedral, there's only 6 things here, doesn't octa mean 8? Well, an octahedron is an 8-sided figure. It's really like 2 square-based pyramids that are interlocked at their bases, and I'm talking about this being the square and these being the tips of the pyramid. If you know that a pyramid has 4 faces, we've got 2 of them here. That means we've got 8 total faces, which is the shape of an octahedron. So each of these atoms is at the vertices of an octahedron. And again, if you've got 6 things around a central atom and you want them to be as far apart from each other as they possibly can be, this would be the arrangement that you would use. Now what I want to point out here is that all the bond angles are going to be 90 degrees. Because if you look here, what you've got is a square. All of these are in the shape of a square, which means that the bond angles here, where they cross the central atom, are all going to be 90 degrees. There's also going to be a 90-degree bond angle between the ones that make up the square and the ones that also make up the tips of the pyramids, and that's these ones here, and so you get 90-degree bond angles here as well as 90-degree bond angles here and here.